Hello all. So in the last session we have seen what are neural networks and how do we use recurrent neural networks RNNs for processing the sequential data, and also we have seen what are the shortcomings of RNN and how do we overcome the shortcomings using pattern matching, and how CNN helps us with processing sequential data with pattern matching concept, right? So we have seen the basic introduction to CNN and the simple architecture of CNN. So today in the session I would like to discuss about CNN layers. Okay, so as we have seen yesterday in the class, CNN architecture, first step in the CNN architecture is convolutional layers, and then we have pooling layers. So I would like to discuss briefly about in detail about CNN layers today in the session. Okay, so convolutional layers are basically the most important or essential part in the CNN architecture, and the term convolution here is all about pattern matching, which is used for overcoming the shortcomings of RNN. Okay, now how do we do this pattern matching using filters? Okay, so convolutional layers are the most important components in CNNs, and these convolutional layers are basically mathematical operations called convolution to input vectors and produce the outputs. Okay, now before we actually start with the layers, we will understand what is convolution. Okay, now understanding convolution requires the basic knowledge of linear algebra, as all of us know about it. Okay, now consider, for explaining or understanding convolution process more in detail, let us consider grammatically deduction example that we have seen in the last sessions, right? So to recap our neural network architecture that we have applied on grammatically detecting sentences, we have taken four words: I, you, am, are, right? So we have taken these four words and we have calculated the word embeddings of these four words, right? So if I want to form sentences using these four words, let me take let me combine two different words forming four different sentences. So they are I am, I are, you am, and you are. Okay, so what we do here, as you can see here in the picture, is I take the words, that is I, you, am, are. I'll take the corresponding embeddings for that, and for each embedding we will produce a pattern. Okay, when you talk about this, we will produce black dot for -1 and white dot for +1. Okay, please understand this. Okay, so we will draw a circle for each pattern, that is -1 black circle and 1 for +1. Okay, white 1 for +1. Okay, now this is all about representing the word vector in pair of circles. Similarly, when you take two word sentences, that is I'm combining I am, I are, you am, you are. Okay, so for this we take two word embeddings x1 and x2, and for the same thing I'm going for pattern. Okay, so here our task is to mostly concentrate on pattern recognition, where the network learns from these black and white patterns, which corresponds to understanding whether the sentences are grammatically correct or not. So here, as you can see, when I form two words, I am taking patch of two vectors, that is four circles here. Okay, and the desired output is something like this. It gives you 1 for grammatically correct sentence and 0 for grammatically incorrect sentence. As you can see, the first sentence I am and the last sentence you are correct, grammatically correct, so we have one output for both of them. And for the second and third case, they are grammatically incorrect, that is I are and you am, therefore we have output as 0. This is the desired output. Now let us see how do we implement this. Now let's think of a filter of the same size. Okay, as you have two circles each on this pattern, let us think we apply a filter of same size. Now what we do here is, each circle of this filter is either black or white, corresponding to the values -1 and 1. Okay, now when you look into the pattern through this filter, we will determine whether the pattern is the one you're looking for. Okay, filter is just a extra layer that we put upon the desired one. Okay, now when you do this by putting the filter over the pattern and count the number of color matches between the two, for each of the four positions you get a score of +1 if the colors matching and a score of -1 if they don't. Okay, when I talk about colors matching, that is +1, we have black with black or white with white. When the colors are not matching, that is black is overlapped with white or white is overlapped with black, we will get a score -1. Okay, let us see, understand that. So as you can see here, this is the pattern and this is the filter. I am applying this filter on this particular pattern where I get my scores. Okay. Now as you can see, I am taking two different patterns. This is one type of filter I am applying where in two cases I am taking all blacks, in two cases I am taking all whites. Now when you look into the right hand side of the figure, as you can see, I am applying the filter which is exactly matching to the pattern. So my score is 4. When you take exactly the opposite of the pattern, the filter opposite of the pattern, then we get the score as -4. Okay. So the score varies from -4 to +4. That is sum of 4 scores. Okay. Now the score you get may vary depending on the pattern and the filter. Okay, the score here that we get depends upon what pattern are you taking and what kind of filter are you applying on that particular pattern. Okay, as you can see in the figure, the score becomes larger. The score becomes larger if the filter matches with the pattern, and the score becomes smaller if the filter does not match with the pattern. Okay, this is very important. Okay, now how do we do this? We do this by putting the filter over a pattern and counting the number of color matches between the two. For each of the 4 positions, you get a +1 if the colors match and -1 if they don't match. Okay. Now, in more general, if you have an input sentence of arbitrary length, what do? We slide a kernel over the sentence from left to right, right? Now, once we do this, we repeat this process applied to 2 consecutive words. As you can see here, each filter is applied for 2 different consecutive words to produce a sequence of scores. So I am getting my sequence of scores. For 2 word vectors, I am getting 1 score. For this 2, I am getting another score. For this 2, I am getting another score. And for this 2, I am getting another score. Okay. Now, here the kernel covers 2 words. So it is said to have the size of 2. Okay. Also, because there are 2 dimensions in the input embeddings, the number of kernels input channels length is 2 here. Okay. Mainly note that the reason embedding diamonds are called channels is because CNNs are most commonly applied to computer vision tasks where the input is often a 2D image of different channels that correspond to different intensities of different colors. Okay. Now, also, when we talk about the computer vision task, kernels are basically the 2-dimensional and move over the 2D input images, which is called as 2D convolution. When you talk about NLP applications, however, the kernels are usually 1-dimensional and have only one size, or you can go for 2D, or for in more advanced applications, you can also go for 3D. Okay. Now, once I am done with pattern matching using filters, that is the convolution layers, I apply this to the activation function. So here we use ReLU as the activation function. Okay. So once, see, I am taking the words, I am giving the word embeddings, I am forming the pattern. Okay. I am done till this. After this, we will use the filter as shown in this particular second figure. Okay. Once I am done with these 2 tasks, we will go for calculating the score. Okay, so let me take 2 kernels here. Okay, as we have taken this kind of filter and this kind of filter, let us take 2 different kernels. Okay, so here on we'll call kernel 1. Okay, for each and every pattern we call this filter as kernel 1, and we will match with the patterns. Okay, now as you can see, when I match my kernels with the filters, I get some desired score. But this desired score is not, sorry, I'll get the score 1. But this score 1 is not matching with my desired scores. Here score 1 is 400 minus 4, and here the desired score is 1001. Here I have negative values. Okay, let's forget about the magnitude of the scores, that is negative values. And for now, let's focus only on the signs, positive and negative. Okay, let's forget about the magnitude. 4 and 4 are same. Now let's focus on the sign. The signs for the first 3 patterns, okay, between score 1 and desired. Okay, the first 3 patterns between score 1 and desired are positive, whereas for the 4th one it is negative, right? For the last one it is different. To score it correctly, that is to get a positive score here for the last case also, we need another filter that matches the last pattern exactly. Okay, so now let's apply different kind of kernels. Okay, here I am applying different kind of kernels, as you can see in the figure below. Now let's call this as kernel 2 and let's calculate score 2. Okay, so depending upon how we calculate this, we got the result. Okay, now kernel 2 gives the correct scores. As you can see, kernel 2 gives the correct scores that match the signs of the desired ones for the last 3 patterns. Here it was first 3 patterns, here it is last 3 patterns, but for the first one it is -4. Okay, but if you observe figures below very carefully, when you observe, these two figures very carefully. Okay, it looks we could get closer to the desired scores if there is a way to somehow disregard the output when a kernel gives negative scores and then combine the scores from multiple kernels. Here in this case, for the last one, for kernel 1, the score 1 last column is negative. Here in case of kernel 2 and score 2, the first column is negative. So we will combine the scores from multiple kernels. So how do we do this? In order to for combining this, we use a simple function. Okay, in simple Python, we write a function which says define f of x. If x is greater than 0, return x, else return 0. As simple as that. Okay, or even simply we can use max function and say define f of x, return max of 0 or x. When you apply this, okay, here this f, so I am taking two word embeddings, pattern, kernel 1, score 1, and I am applying function of score 1 with which I can eliminate my negative values. Okay, so similarly applying ReLU, this function f of score 2 is nothing but ReLU function. Okay, applying ReLU to score 2. Okay, now this function that we are applying to score 1 and 2 is called as rectified linear unit or ReLU, which is one of the simplest yet most importantly used activation function in machine learning, deep learning or NLP applications. Okay, now it is often used with convolutional layer. Although it is very simple, it is still an activation function that enables neural network to learn complex nonlinear functions. Okay, now look at this. After we combine these codes, okay, now we got F1 score, F2 score and the desired outputs. Now we will combine them together by summing and adjust the range by dividing by 4. Okay, so I'm combining these two tables into one, saying F1 pattern, kernel 1, kernel 2, F score 1, F score 2, and I'm combining 4 plus 0 by 4, that is 1, 0 plus 0 by 4, 0, 0, and then 1. Okay, so in this way we will sum and add, wherein we get the combined results equal to the desired results. Okay, so all we did so far was design kernels and match the patterns we want to detect and then simply combine the scores. Okay, so compare this to RNN example where we needed to use some complicated numeric computation. Okay, here in CNN we are simply performing that by using pattern matching. Okay, now once we are done with this convolution, I am taking a sentence, converting that into word vectors, applying convolutional layers. Once we are done with convolutional layers, we go for pooling layers. Okay, so the input to a CNN can be of arbitrary length. Okay, CNN should not only detect the patterns. Here convolutional layer is actually responsible for detecting the pattern, but CNN layers are not only responsible for detecting the patterns, but also they should find the potentially large amount of noise in it, right? So we use the slide kernel from the sentence from left to right, and the kernel is repeatedly applied over two consecutive words, as you can see here in the figure, to produce sequence of scores. Okay, now once I'm done with this input kernel applying a ReLU and I get the score, what do I do next? So here the question mark. So how to position this particular thing to get the desired code? Okay, so the operation here needs some properties that we are going to look into now. Okay, so the simplest thing that we do is here in pooling is either take the maximum value or take the average pooling. The simple thing that we can do is taking the maximum of the score. So here the largest score is 4, hence in place of question mark I'll apply school. This aggregation operation is called as pooling. Either go for average pooling or go for max pooling. Okay, now once the pooled score will be once the pool score is calculated, we fed that to a linear layer, optionally combine the scores with the other layers and use the predicted score, and the entire process is illustrated in the figure here. We take the input, give it to kernels, apply filters, give the activation function, calculate F scores, perform pooling, max pooling, and then apply to the linear layer, and then give it to a softmax function, and then get the desired output. Now this is a fully functional CNN. Okay, now the output from the linear layer is fed to softmax. We use the softmax to produce the probability distribution over the labels. Okay, so the predicted values are then compared with the true labels to produce the loss function, and if the loss function is more, we optimize the network using different parameters. Okay, so because the kernels in the CNN do not depend on each other, and like in RNN where one cell needs to wait until the previous self-finish processing, CNNs are computationally efficient. This way we can overcome the disadvantage of RNN using CNN. And secondly, as GPUs can process the kernels in parallel without waiting on other kernels output, due to this property, CNNs are usually faster than RNNs of similar size. Okay, so this is all about your CNN layers. So basically understand that we have these two different layers. One is convolutional layer, pooling layer, and give it to linear layer, and then softmax function for probability distribution over the labels. Okay, so this is all about CNN layers. Thank you.